Hi, I've gotten a couple of emails from students concerned with calculations in Lab 5, the copper sulfate lab, and they were specific about not being familiar with what the mole is. So that maybe I just go over that real quick. Simply put, the mole is a number. It's 6.022 times 10 to the 23rd. Okay, and it's exactly the same as saying a dozen is 12. Or a million is, well, a million. Okay, its utility comes about because we use it in chemistry to convert from easily accessible amounts, namely masses, into numbers of particles. So this number comes about is it's the number of carbon-12 atoms So the mole comes about because it's the number of carbon-12 atoms. It's an isotope of carbon that has 6 protons and 6 neutrons. All carbon has 6 protons, most has 6 neutrons. In any case, that isotope of carbon-12, if you had 12 grams of carbon-12, the number of carbon atoms is the mole. Okay, so this actually goes out to as many digits as people can measure, but for our purposes, none of that matters. That sort of matters. Where it gets more useful is that if I were to pick any element, so if I were to look at, say, hydrogen, hydrogen has an atomic mass of 1.008. Now on the periodic table, this is an average of all of the different isotopes. So most hydrogen has all hydrogen has 1 proton. Most hydrogen doesn't have any neutrons, but some does. If it has a neutron, it's called deuterium. If it has 2 neutrons, it's called tritium. In any case, this number here is the average atomic mass of hydrogen. We can give it units of atomic mass units. So say hydrogen has a mass, one atom has a mass of 1.008 atomic mass units. Or what we can do is say if we had a mole of hydrogen, so 6 times 10 to the 23rd of these, it would be 1.008 grams. So this right here doesn't list any units, but in chemistry, we typically start using it as grams per mole. And again, somewhat arbitrary, but that way we're all speaking the same language. Okay, in the lab, you were supposed to calculate some percentages, so percent by mass. So let's do a different example. And I'm going to look at H2O. Okay, so H2O has 2 hydrogens and 1 oxygen. All right, so my 2 hydrogens are going to give me 1.008, 1.008, and then the oxygen 16.00. So if we round that off a little bit, we're going to get that water weighs 18.02 atomic mass units, or grams per mole. Okay, if I needed to go a little further with that and calculate the percent of either of those elements in water, what I could do is take the mass of hydrogen over the mass of H2O. And it doesn't matter how much I have, right? If I have 10 molecules, or I have a billion molecules, or I have a mole of molecules, the ratio will be the same. So I'm just going to use the grams per mole data, and I'd say, oh, okay, there's 2.02 grams of hydrogen for every 18.02 grams of H2O. And this works out to be 11.2%. So water is 11.2% hydrogen by mass. In experiment 5, where you were to calculate the percentages of copper in the copper sulfate, we had 2 calculations. One of them was the experimental, which was actually taking those numbers that you were provided with. So it was the 0.27 grams of copper divided by the 1.1 grams of copper sulfate. So whatever that worked out to be, 25% or something. And then the one that I suspect is giving people more trouble is this theoretical percentage. So just like we calculated the percent hydrogen in water, in this calculation, we're calculating the percent copper and copper sulfate based on the formula. So in our numerator, we'd go to the periodic table and we'd see that copper weighs, where's my periodic table? So copper, number 29, weighs 63.55, and the 63.55, and in the numerator, you've got the copper at 63.55, you've got sulfur at 32.07, you got 4 oxygens at 16 each, you got 10 hydrogens at 1.01 and 5 more oxygens again at 16. So that whole sum here is going to be the molar mass, or the formula mass because it's ionic, of the copper sulfate pentahydrate. And that would be the same calculation that we did to figure out that water has 18 grams per mole for its molar mass. So again, this calculation would take the atomic mass of copper divided by that sum of masses of the copper sulfate, and again, you should get somewhere in the neighborhood of 25% there. All right, hopefully that's clear. Good luck.